For number 10 on the practice exam, uh, hopefully you recall that after the partial fractions was section 7.6 in our book. And what 7.6 did was just some general integration strategies where you had to decide the best integration technique. So 7.6 is supposed to be represented on this practice test by problems 10 and 11. Now, the way I was thinking about it is that since we already have the problems with partial fractions that's representing 7.5 here, and the problems with trigonometric substitution, that's section 7.3 and 3 through 5, and then our trig integrals, that's section 7.2 up here, I figured I would go back and use other techniques of integration on these two. So most notably, our other integration techniques are integration by substitution and integration by parts. So you should expect to see that in problems 10 and 11. So what I did for this number 10, we had the integral of sine cubed over cosine to the sixth. Even as early as our top problems where we had odd powers of sine and cosine, even though that this isn't just a trig identity problem, a trig identity does help, because I know that sine cubed theta could be written as sine squared theta times sine theta, and sine squared theta could be rewritten as 1 minus cosine squared. Well, and of course the angle is x, so 1 minus cosine squared x. Now, if I do that, I can put the remaining sine of x over here. Remember, this is sine x over 1. That sine x is implied to be in the numerator. Better written over here times the dx, because now this puts it in a format where I can say, oh, I can let u equal the cosine function, and all of this is going to be a function of u, and then the derivative of cosine is the negative sine of x dx. All I have to do is multiply my inside by a negative and multiply my outside by a negative, and I can replace this with a du. That's what I did in the next step. So the du replaces the negative sine of x dx. I have my negative on the outside. And then this expression just becomes 1 minus u squared over u to the sixth. Now you need to remember, anytime you have a binomial divided by a monomial, that monomial can distribute to both terms in the numerator. So this becomes 1 over u to the sixth, which is better written as u to the negative sixth, minus u squared over u to the sixth, which is better written as u to the negative fourth. Now I need to integrate the negative integral of this function of u. Well, easy, power rule. I'll keep my negative on the outside. Power rule tells me to add 1 to the exponent, divide by that new exponent. So I get u to the negative fifth over negative 5, and it would become minus u to the negative third divided by negative 3 plus your constant of integration. Now, in that first term, we know it's going to be minus a negative, so it's going to be positive. And I'll have 1 over 5 u to the fifth, where u to the fifth is cosine to the fifth x. So 1 over 5 cosine to the fifth x. My next term on the inside would be positive, but then this makes it minus. So I say minus, and my numerator again is going to be 1. I'll have a factor of 3 and u cubed in the denominator, where that becomes cosine cubed. And then, of course, plus our constant of integration. I thought that this looked a little sloppy with the minus sign in that fraction, although it's fine. But I just cleaned it up down here to make sure it looked like a better answer. So 1 over 5 cosine to the fifth x minus 1 over 3 cosine cubed x plus your constant of integration. Now, the next problem, again, this is out of section 7.6, where we're supposed to try general integration strategies. The very instant you see a natural log in a problem, that should set off kind of red flags in your head. Ooh, I am going to use integration by parts on this problem. So if I have the integral of the natural log of 1 plus x squared, I can say, well, all right, the only term in there, natural log of 1 plus x squared, has to become u. Then that means that dv has to be the understood 1 dx. And then I take the derivative of u. and say, well, the derivative of every single logarithmic function in existence is 1 over what's inside the logarithm times the derivative of what's inside the logarithm. Well, my numerator is the derivative of what's inside, that's the 2x. So many students forget this part right here. They'll say derivative of natural log of x is 1 over 1 plus x squared. You're forgetting the chain rule if you're thinking that. The chain rule says you must multiply by the derivative of the inside, and that derivative of the inside goes in the numerator. And of course, this derivative is with respect to x. Now, when I integrate, I'm integrating 1 with respect to x. Of course, that's x. Derivative of x would give me 1 dx. Now, I have my integration by parts set up, integration by parts formula. The integral of the natural log of x dx should be u times v minus the integral of v du, v do. So u times v, x, natural log of 1 plus x squared, minus the integral of v du. So I knew that that would give me minus the integral, and I would have 2x times x, so minus the integral 2x squared over 1 plus x squared dx. As soon as I get to this part, I'm thinking, okay, integration by parts probably not helpful anymore. Integration by parts is only helpful when we have a product or just one term in there. It's not really helpful when we have a quotient. So as soon as I get this quotient, I can say, the only time I can integrate is when the degree of the numerator is less than that of the denominator. Anytime it's equal or greater than the denominator, I should use long division in order to simplify out this expression. That's what I do. So over here in the red, I said, well, I'm going to take 1 plus x squared, divide that into 2x squared. So I just thought, well, how many times will x squared go into 2x squared? Of course, 2 times. 2 times x squared is 2x squared. 2 times 1 gives me the 2. Now I subtract that group out. 2x squared minus 2x squared cancels. That's the point. We always have to cancel that first term. But then we're going to have minus this positive 2. So we get a remainder of negative 2. Now let's be very careful about what to do with that remainder. So I go down here, and it's good notation to always say I is equal to. I is just your original integral problem. Let's see if I can clear up. That's a little bit blurry. That's a little more crisp. So I is our original integral problem, and it's equal to the original u times v, x, natural log of 1 plus x squared. And then we can say, all right, minus this. Well, this divided evenly and left me a whole number value of 2. So I can say, well, it's minus 2 with respect to x. And then it would also, since this is inside of an integral, it would be minus, what's the rest of the part in the integral? Well, it had a remainder of negative 2. That negative 2 is still remaining to be divided by 1 plus x squared. So the minus sign's out in front only because this was minus. You say every part, that's the answer here, is going to be inside of an integral that is subtracted. So I have minus the integral 2, that divided evenly with respect to x, and then minus the remainder, negative 2, divided by what was originally divided by 1 plus x squared. Now, I keep in mind here, well, I know the integral of 1 over 1 plus x squared is the inverse tangent of x. So this is just a multiple of 2 of that. I know I could distribute that, or factor, not distribute, but I can factor that negative 2 to the outside. It would be plus 2 times the integral of 1 over 1 plus x squared. So then we can say, all right, this part was already done. And then this part has the simple integral of minus 2x. And then this part's going to be plus, because the negative 2 factoring out is going to make it a plus 2. And then I'll be left with an inverse tangent of x plus your constant of integration. Nice problem. Now, for the next one here. This is asking us to write the following improper integral in proper form and integrate to determine a solution. Please keep in mind, in this problem, just like I wrote in red here, I am not simply looking at your final answer. A lot of these problems, you don't have to have the work laid out exactly like I do, although I take great pains to really try to make sure I show my work well in these problems to where anyone should be able to follow it. But you don't have to do the work like I do in the problems. As long as you can get to the answer and have some semblance of supporting work, it'll be fine. Now, that's not necessarily the case for number 12. Part of number 12 and part of what this section 7.7, I believe, was trying to get us to do is to be able to take improper integrals and write them as proper integrals. So I need to see that you made it a proper integral. In this problem, whenever you look at it, you say, well, okay, he's not going to give me anything. And if you remember section 7.7, they didn't have hardly anything in that section that was hard to integrate. Most of the problems were pretty simple to integrate. I'll give you something pretty simple to integrate, just like this. However, it's going to be undefined at one of its limits of integration. And whenever you look at this just real quickly, you say, well, it's a fourth root in the denominator. I know it can't have a negative number in it, which we don't have to worry about that, but it also can't have a zero, and that's what we do have to worry about. Because if you try to plug in your lower limit of integration, you say, well, the function we're trying to integrate is undefined at its left-hand limit. And sometimes students are like, well, wait a minute, that you can't work the problem. The whole problem's undefined. No. If you think about what the integral is supposed to represent anyway, the integral represents the area under the curve starting at -2 and ending at 14. So the fact that that left-hand limit isn't defined, irrelevant. The area under the curve is still going to be accumulated just to the right of -2 and all the way up to the 14. So I can say, well, all right, I know that -2 would give me an undefined value. So to make this a proper integral, then I have to say, well, I'm going to integrate all the way down to -2. And whenever it's the lower limit of integration that's undefined, we always must do a right-hand limit. So you can't just say, well, can I just put the limit as a approaches -2? No, because by definition, this would mean that you're approaching -2 from the left and the right-hand side. We are not approaching -2 from the left. We're only approaching -2 from values above -2. So we're approaching -2 from the right. If, for example, this had been undefined at 14, and I could have easily done that, it'd just been the fourth root of, let's say, x minus 14 down here, then you'd have said, well, all right, then it's, well, that would have created other problems because you'd have had negatives on the inside too. So you can kind of forget that example. But hypothetically, if it were undefined at 14, you would approach the limit as as a approaches 14 from the left. But in this problem, 14 is not an issue. The -2 is. So I had to approach -2 from the right. Now, on the inside, it's an easy group to integrate because anytime you have a linear function to a power, you're going to be able to use the power rule and integral chain rule for this. So I can say, okay, no problem. And I'll just think about this as the group x plus 2 to the -1/4 power. And then whenever I integrate, my integral power rule says I'll add 1 to that exponent, becomes x plus 2 to the 3/4 power, divide by that new exponent. If you divide by 3/4, then you're multiplying by 4/3. Technically, you would also divide by the derivative of what's inside of this group, but that's just a 1, so that doesn't contribute anything. Now, we're going to take, and I needed to see this limit still in this step, the limit as a approaches -2 from the right of this integrated expression evaluated from a to 14. Now, when we plug in a 14, that's just going to give us 14 plus 2. That's going to be 16. The fourth root of 16 is 2, and then 2 cubed is going to be 8. We're going to have 8 times 4/3. That's going to give me my 32/3. Now, that's what I did here. From this step to this step, I really didn't do a whole lot other than, and you wouldn't have had to have written this step. I would have been fine with this. But what I did in this step was I put it back in radical form since the original problem was in radical form. So I do like this. However, that would have been fine. So then I can just say, well, at the upper limit, when we plug in our 14, that's what I was talking about up here. We know that this is going to become the 4th root of 16, which is 2. And then we're going to have a 2 cubed. We're going to have 4 times 2 cubed in the numerator divided by 3. Now my lower limit is where we'll have to consider the limit as a approaches -2 from the right, and you'll just plug an a in for the value of x. And now if you think about it, well, as a approaches -2, that inside part is going to become -2 plus 2. Well, that becomes 0. 0 cubed is 0. The 4th root of 0 is 0. So this is all just 4/3 times 0. That's what I'm trying to show right here. So the only answer we get is from the upper limit. We get our 32/3 minus 0 for a final answer of 32/3. Now, for the next problem here, this should start chapter 8. And I just put one problem out of chapter 8. You can tell I wasn't too much of a fan of chapter 8. I didn't think it was that critical. But it does give us one arc length problem. Find the arc length of y equals 2x to the 3/2 from x equals 0 to x equals 5. Okay, so our arc length formula is that the arc length, and you do need to know this, is that it's the integral of the square root of 1 plus the derivative squared integrated with respect to x. So we can say, all right, then whenever we do an arc length problem, it's pretty straightforward. We'll take the derivative of the expression that we're working with. 3/2 times 2 gave me a 3, and then I dropped the power down to 1/2. So derivative is 3x to the 1/2. When you square that derivative, we know 3 squared is 9, x to the 1/2 squared is x. So I get, well, the derivative squared is just 9x. Then my arc length from 0 to 5 is the integral from 0 to 5 of the square root of 1 plus the first derivative squared. So again, just like the last problem, you're like, oh, it's a nice linear function raised to a power. I'm thinking of this as 1 plus 9x to the 1/2 power. Whenever we integrate that 1 plus 9x has the power increased by 1 to 3/2. We divide by that new power, and we divide by the derivative of the inside linear function. So you say, well, we're also going to have to divide by 9. Now we need to still evaluate this expression. This is the correct integral, but now we need to evaluate it from 0 to 5. I just simplified before evaluating it. We know that this is going to become the square root of this group to the 3rd power. And my denominator would be 27/2. So if you divide by 27/2, then you're multiplying by 2 27ths. So I said 2 27ths on the root of 1 plus 9x raised to the 3rd power. And then when I plugged in the 5, I knew that this was not going to work out nicely as far as nice numbers. It's going to be an irrational number, so I chose to keep the roots. When I plugged in the 5, it gave me 9 times 5 is 45 plus 1 is 46. So I can say, well, that's 46 cubed. I don't want to think about the large number 46 cubed is. So instead, I just said, well, it's the same thing as the square root of 46 times itself 3 times. Square root of 46 times the square root of 46 is 46 times a 3rd square root of 46 gives me that root of 46. So this is the square root of 46 to the 3rd power. I have my 2 27ths out in front. Now I need to subtract the lower limit, and I can say, well, the lower limit's when I would plug a 0 in here. Clearly, when you plug a 0 in, you're just going to get the square root of 1 cubed, which is just 1. Then you can say, all right, then we'll have 46 on the root of 46 minus 1. All of that, I put that times 2, and then I divided the whole thing by 27 to make one nice answer. And I do want an exact answer here. I don't want a wimpy decimal approximation to this problem. And we'd be done at that point. Good problem. Whoops. Up next here. Here we go. So for number 14, says find the summation of the following telescoping series. Now, some of you on your Achieve assignments had some really challenging telescoping problems. I was working sum with you, and it took like 10, 11, 12 terms before any cancellation started to occur. I'm not going to give you a problem on a test like that. If you're going much beyond the third or at most the fourth term and you're not seeing cancellations, it's because you're not doing something correct. So in this one, automatically when I see, oh, my denominators differ by 2, I'm going to have 2 terms, and then at the third term, you're going to start seeing cancellations. So I can just tell that just from looking at the initial problem, and you can too. You can just say, well, however many they differ here, you're going to have that many terms without cancellations, and then the cancellations start to occur after that. So looking at 14 with you, when we do the telescoping series problems, you just say, well, all right, we can't simply just start plugging in numbers. Like when you plug in a 3, you'd say, well, that'd be 1/3 times 1, it'd be 1/3. Now plug in a 4. Your next term would be plus 1/2 times 4. So you got 1/3 plus 1/8. Plus your next term would be when you plug in a 5, that'd be 1/15. So you're like, well, what is this going to? Well, we can find the sum of that series, but not by just plugging in values like that. So you have to say, well, we need to rewrite that general term as the sum of 2 simpler fractions. So we use the method of partial fractions and say 1/n-2 times n equals some constant a over n-2 plus some constant b over n. Then we can say, all right, multiply by that least common denominator. When you do that on the left, you get a 1. When you do that on the right, you'll have a times n plus b times n-2. Now, in order to solve for a, you should be able to set n equal to 2. That's what I do right here. When I set n equal to 2, I know my left-hand side is still going to be a 1 because it doesn't have an n to plug in. And on the right-hand side, you'll have 2a and you'd have 0b. So you have 2a is equal to 1, thus a is equal to 1/2. Now, if I let n equal 0, I should be able to solve for b. When I do that, my left-hand side is still 1. I forgot to put a 1 there for that part. The left-hand side is still 1. And then we get on the right-hand side, when you plug in the 0, you'll have 0 minus 2, negative 2b is equal to 1. And then you can say, well, all right, then b is negative 1/2. Now that I have my answer for a and I have my answer for b, I should be able to go in and work this problem. So here's what I'm saying. I'm saying that this original summation is equal to, and I know it would be the sum of these two, since they both had a 1/2, I'm going to go ahead and factor that factor out. And I think it's best to. You don't have to, but it's best to. So I said, I'm going to factor a 1/2 out of that summation. When I do that, my term a would just become a positive 1. I get 1/n-2. And then my second term, instead of a negative 1/2, it's just going to become a -1. So plus a negative 1 becomes -1/n. Now, this should allow me to see what the sum of this series is much more efficiently. So I'll say, okay, then the sum of the series is 1/2 times, this would be my first term. The first term is when you plug in an n equals 3. So you'd say, well, it's going to be 1/3 minus 2, 1/1, minus 1/3. That's the first term. Your second term is when n is 4. When n is 4, you'll get 1/4 minus 2, or 1/2, minus 1/4. Now, after that, I said, well, here's my third term. Now, up to this point, I didn't see any cancellation at all. So the red came in later. Once I got to my third term, I can say, well, the third term is going to be when n is equal to 5. When n is equal to 5, your first term is going to be 1/5 minus 2. It's going to be 1/3. Your second term is going to be minus 1/5. So this is where I can see the first portion of every term after this is just going to cancel with the second portion of a preceding term. So like I know the first part of the next number is going to be 1/4, and it's going to be a positive 1/4. It's going to cancel with that minus 1/4. The next term would have a plus 1 over 5. That's going to cancel with this minus 1 over 5. So I can say every second portion of the number is going to cancel for these with a first term in a later number. But I can say, well, the first portion of these first two terms will never cancel out. Now, similarly, the last portion of the very last two terms would also not cancel out. So you'd have minus 1 over n minus 1 and minus 1 over n. Why am I not concerned about those? Why did I just put plus dot dot dot? Because as n goes to infinity, 1 over n goes to 0 anyway. So those last few terms that don't cancel, irrelevant. The first few terms that don't cancel, very relevant. They have a value that's not 0. So the sum of this series is simply 1/2 times 1 plus 1/2. 1 plus 1/2 is 3 over 2. 3 over 2 times 1/2 gives me a summation of 3/4. Gorgeous problem there, guys. Next one. When we're looking at it, and hopefully I'll go to the correct thing here. Yeah, here we go. When we're looking at it here, number 15 is asking us to use the geometric series test. So geometric series, you need to be looking for a common ratio. I mean, it's extremely obvious in this problem. You can say, hey, the way you get from the nth term to the nth plus first term is you'll continually multiply by an additional factor of -3 over 4. So since this does have a common ratio, and that common ratio, the absolute value of it is less than 1, this is a convergent geometric series. So I know it converges. Now, what would have made it not converge? Well, I could have made that -5/4. That would not converge. It's going to diverge off, and it wouldn't have a sum in that case. It's going to diverge, and we don't even know if it's going to positive or negative infinity because it's going to continually alternate since it would be a -5/4. Now, for this problem, though, what I would go in and do to show my work is I would just say any convergent series always has a sum of c over 1 minus r. Now, c just stands for your very first term, your constant, that doesn't have the common ratio factored into it. Well, you can get the constant in the problem by just plugging in the bottom value in your series. Now, please don't always assume that that bottom value is 0. You have to look at the particular problem to get what the bottom value is. So you can say, well, my constant, my c value, is when I plug in a 0 here. If I plug in a 0, then all of that's just 1, any number to the 0 power. So you'll have 7 times 1 is 7. C is equal to 7. Now, 1 minus the common ratio. Every term after that very first 7 is going to be continually multiplied by a higher and higher power of -3/4. So in order to get from the first term when n is 0 to the second term when n is 1, you multiply by -3/4 once. In order to get from that second term to the third term, you'd multiply by -3/4 twice. So you say every single term thereafter is multiplied by -3/4. It's your common ratio. So 1 minus r, r is a -3/4. So the negative does have to take place in your formula. So you say, well, that's going to be 1 minus -3 over 4. In order to simplify that, I'll multiply by the denominator 4 here to get rid of that fraction inside the fraction. When I do, my numerator is 28, and my denominator would be 4 plus 3. So it's 28 over 7. I get the sum of this series is 4. That is a convergent geometric series, converges at 4. Now, for the next one, let's see here. For 16, here we go. Oh, it's just the test for divergence. Now, what I need you to remember for the test for divergence, this should be an extremely easy answer. But the problem that I see students do with this one is they want to think the test for divergence does more than it does. The test for divergence can only tell you if a series diverges. It can never tell you if a series converges. So you say, well, what does the test for divergence do? Well, it says if the limit as n approaches infinity of the general term, which we typically call a sub n, if the limit as n approaches infinity of a sub n does not equal 0, boom, the series can, boom, the series diverges, almost said converges. Now, what if the limit as n approaches infinity of a sub n is equal to 0? We don't know anything. It could converge or diverge. Please don't say too much with the test for divergence and say, well, by the test for divergence, it converges. I will mark that wrong all day. The test for divergence never says something converges. It can only tell you if something diverges. Now, let's look at that within this problem. So here was the series I gave you. Now, what does the divergence test do? It just says take the limit as n approaches infinity of the general term. The limit as n approaches infinity of this general term here. Now, this is slightly tricky here. I want you to remember back to Calc 1, you'd say, well, okay, anytime you have a limit going to infinity, anytime the degree of the variable in the denominator is greater than the degree in the numerator, it goes off to 0. Now, the reason I say slightly tricky is because somebody could say, well, it's the same degree. And I'd say, no, it is not. This rational function has degree 1 in the numerator because it's the square root of n squared, and it's degree 2 in the denominator. Now, if you algebraically showed this, you would divide the denominator by n squared, and you'd have to go into your numerator and divide everything by inside of that square root. You'd have to divide by the equivalent of n squared, which would be inside the square root, you'd be dividing by n to the 4th. And so when you do that, you would show that the numerator is 0, the denominator simplifies down to 3, you get a limiting value of 0. We do not have to show that algebraic limit strategy. You can just say, degree of the denominator is greater than the numerator. The answer is 0 if it's going off to infinity. Done. Now, well, shouldn't say done. You still have to do more for the problem. Since that answer is 0, what the divergence test says is that, well, it could converge or diverge. The divergence test doesn't tell you anything. It's just saying the divergence test, since the limiting value is 0, it could diverge, but it also could converge. So that's all I need right here. Now, reading into it a little more, if that limit had not been 0, for example, what if I would have said this was the square root of 5n to the 4th plus 8 over 3n squared? Had this been an n to the 4th inside the square root, your limiting value would have been the square root of 5 over 3. And then in that case, you'd have said, hey, the limiting value is not 0. This series diverges. Period. End of story. You'd have made this statement right here, since the limiting value was not 0. Now, if you know that the limiting value is 0, it doesn't tell you that it converges or diverges. So knowing that the limiting value is 0 is not conclusive evidence that the series converges. So it just says that it's not, we don't know that the divergence test is inconclusive. Now, for number 17, we're using the, looks like the comparison test. Let me go back and see. Yes. It says use the p-series and comparison test to determine the convergence of 1 over n squared plus 5. Okay. So the whole concept of the comparison test, especially when you're using a p-series, we remember the p-series, it's whenever you have 1 over n to the p inside of a summation. And it's only convergent if that p is greater than 1. The denominator has to get large quickly in order for that series to converge down. So you say, well, okay, it has to be 1 over n to a power greater than 1, like 1 over n to the 1.1, 1 over n squared, 1 over n cubed, 1 over n to the 4th. All of those converge. Something like 1 over the square root of n diverges because it's a p-series of p equals 1/2. Now, in this, I'm supposed to look at the problem I have and say, well, it's essentially a p-series with p equals 2. Now, it's not technically a p-series because you have another term down there with it. But I can just say, well, I'll use the comparison test And by the comparison test, since I already know, well, this is comparable to a P series P equals 2, and I know a P series P equals 2 should converge, the comparison test is only going to be beneficial if I can show that this is smaller than a series that converge. Hypothetically, what if I show that this is larger than a convergent series? You haven't shown anything in that case. Because if you're larger than something that converges, then do you converge or diverge? You don't know. So in order for me to have conclusive evidence in this problem, I must show that this is less than a convergent series. Okay, so I do that. I say converge with a convergent P series 1 over n squared, and that's a convergent P series because the denominator has a power greater than 1. And then I can say, well, all right, since this denominator is always greater than this denominator, think about this. If you have two fractions and one fraction always has a bigger denominator than the other fraction, well, then this fraction is smaller. You started putting real numbers in there, you could say, well, this is like 1 over 6 versus 1 over 1. When n is 2, you'd say, well, this would be 1 over 4. This would be 1 over 9. It's always going to be smaller than that fraction for any value of n between 1 and infinity. So since this general term is always smaller than this general term, then we know our series 1 over n squared plus 5 must also converge. And again, it's because the general term of this series is less than the general term of the series which we know converges. Now, the comparison test, unlike the geometric series test, does not tell you what it converges to or anything like that. It just says it must converge by the comparison test. Now, the next problem here, very quick and easy. If I say the Leibniz test or the alternating series test, I'll give you something like this, and if it's an alternating series test, you have to see the -1 to the power in there. And then what the Leibniz or the alternating series test does is it says, all right, take the limit as n approaches infinity of the non-alternating part. So ignore the alternating sign, the -1 to the n. If you take the limit as n approaches infinity of the rest of that, and if you can show that that limiting value is 0, boom, it's convergent. Now, sometimes students get this confused with the divergence test because they're like, aren't you doing the same thing? No, in the divergence test, if the limiting value is 0, you haven't shown anything. You just shown that it could converge or diverge. Here, if you know the sign is alternating, it is sufficient to show if the limit of the non-alternating portion, if that's 0, it is convergent. Well, what if the limit is not 0? Then it would be divergent. So the alternating series test allows us to come to more conclusive decisions than simply the divergence test. But of course, the divergence test can apply to terms that are not alternating. But because of that, it's not as useful in our results. This gives us a very useful result. If the answer is not 0, diverges. If the answer is 0, converges. Now for number 19. In this one, let me go back and see what the problem asked me to do. It said use the limit comparison test. Ooh, I love the limit comparison test. It's one of our most useful tests. Use the limit comparison test to determine the convergence of the summation from n equals 1 to infinity of 2 to the n minus 5 over 3 to the n plus 52.3. Now, what I want you to do in this problem, little common sense goes a long way in these problems. Whenever you look at this, you just say, well, that minus 5 and that plus 52.3, those kind of seem like wasted values. Well, they are. Just think they really don't impact the size of this fraction as n is getting large. Even if you just put a small values of n like 10 in, 2 to the 10th power, ridiculously much larger than the little stinky minus 5. 3 to the 10th power, that number is enormous and compared to the tiny little 52.3. So these numbers become inconsequential as n goes off towards infinity. And I can say, well, I'm really essentially thinking of this as 2 to the n over 3 to the n. So you say, but it's not just 2 to the n over 3 to the n. You say, no, I know it's not, but I'm going to compare it to that using the limit comparison test. Now, what do I know about 2 to the n over 3 to the n? It could reduce down to 2/3 to the n. Gorgeous! If it reduced down to 2/3 to the n, then it's a geometric series with an R value of 2/3, very similar to what we had right here. You just say, oh, instead of a -3/4, I could just think of this whole function as the group 2/3 to the n. That's what I did. So I said, I'm going to compare that with 2/3 to the n. You add a 2 to the n in the numerator, 3 to the n in the denominator. You can simplify that to 2 over 3 to the n. Now, 2/3 to the n, anytime you have a geometric series, it converges if that absolute value of the r, the value that's continually multiplied, in this case 2/3, if that's less than 1. 2/3 is less than 1. This is a convergent series. Now, what the limit comparison test asks us to do is it says just take the limit as n approaches infinity of the general term of the series we don't know, divided by the general term of a series we do know. And if we can show it's some constant multiple of that other term, now think about the logic here. If we can just show it's some constant multiple, well, if you're a constant multiple of something that has a convergent finite answer, then you also have a convergent finite answer. Well, what if you're infinitely times larger than it? Well, then you're divergent. So as long as this answer is some finite number between 0 and infinity, whatever happens to our series that I'm calling B sub n here is going to be the same thing that happens to this series. So I say, okay, limit comparison test tells me to take the limit of the series I'm trying to work with divided by the series I know the convergence of. So when I do that, anytime I'm dividing by a fraction, I'm multiplying by its reciprocal. So I took the 3 to the n up, multiplied it in the numerator here, the 2 to the n multiplied the denominator. That's where this came from. And then I said, well, all right, now that's going to give me a 3 to the n times 2 to the n. Anytime you have the exact same exponent, you can multiply the bases and say, well, that's going to give me 6 to the n. Same thing down here, 2 to the n times 3 to the n is 6 to the n. Every other term in there is going to be infinitely times less than it. So just to show that, I said, well, plus dot, dot, dot. Those terms are going to be inconsequentially times smaller, so they're not going to impact the overall limit. Now, when I take this limit, well, numerator has a 6 to the n, denominator has a 6 to the n. Clearly, that's going to reduce down to 1. So what this is saying is that essentially, as n goes to infinity, the size of this series is, it's essentially a multiple of 1 of this series. So they're the same size. This series converged, thus this is conclusive evidence that this series converges. So we say, since the limiting value is 1, which is a finite number between 0 and infinity, I just showed that 1 is between 0 and infinity, and the series B sub n converges, then the series in question up here also converges. Now, if my series B sub n had been a divergent series, well, then this would also diverge, because what if you're a constant multiple of something that doesn't have an answer? Well, then you also do not have an answer. So if whatever happens to the series that I understand also happens to this series, if it's just some constant multiple of it. Now, for number 20, I believe it's the same type of problem, limit comparison test. Yes. Now, while it's the same type of problem, I'm trying to make sure you use it to look at the other types. So this one was a geometric series. This one goes back to a P series, where you say, well, this is essentially a P series with P equals 1 because the square root of n squared is n. So you say, well, the P series P equals 1, that's a divergent harmonic series. So I bet that this problem diverges. Is it enough just to say it diverges? No, you have to show me the work. So now I go in and I try to explain it. Here's the series I'm working with. I'm going to compare that to the divergent p series with p equals 1. It's just 1 over the square root of n squared. So you say, well, 1 over square root of n, that's just 1 over n. Remember, that is our smallest possible divergent series. It'd be 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5. On and on and on. That's going to still diverge off to infinity, even though that fraction goes off towards 0. This would be a case where people would look at the divergence test and say, well, wait a minute, doesn't it converge because the limit as n approaches infinity is 0? No, it still diverges, even though by the divergence test, the limiting value is 0. This harmonic series is still a divergent series, our smallest possible divergent series. Now, whenever I'm trying to compare that with the one in question here, I can say, well, the limit comparison test tells me to take the limit as n approaches infinity of the general term of the series I don't know, divided by the general term of the series I do know. So I say, well, that's the limit as n approaches infinity of 1 over the square root of n squared plus 4, divided by, and I just wrote it as 1 over the square root of n squared. And so then whenever you divide by a fraction, you multiply by its reciprocal. That gave me a square root of n squared in the numerator. And of course, the square root of n squared plus 4 in the denominator. When you take your limit as n approaches infinity of this expression, of course, you're just going to get a 1. Now, again, what this tells us is that as n goes to infinity, the terms in this series are essentially a multiple of 1 of the terms of this series. So you say, well, then I know the terms of this series diverge. That means this series also diverges. That's what I put here. Since the limiting value is 1. Now, don't get hung up on 1. Both of these values happen to be 1. But even if it were 100, or even if it were 1,000, or even if it were 1/2 or 1/3, any number between 0 and infinity is saying it's a constant multiple of that. Then whatever happens to this series happens to this series. This series diverged, thus this series diverged. So you can say since L was a constant between 0 and infinity, and the series B sub n that we're comparing it to was a divergent series, then the series in question also diverges. For number 21, gorgeous problem. We have the ratio test. Whenever we're looking at what we're supposed to do with this one, just use the ratio test to determine the convergence of the summation of -1 to the n times n factorial over 9,999 to the nth power. Cool problem. So whenever we're looking at that, the ratio test, I wrote it out right here, it always asks us to take the limit as n approaches infinity of the absolute value of the a sub n plus first term over the a sub n term. Now, the logic of the ratio test just says that if the limit of this n plus first term over the nth term, if the absolute value is less than 1, that's clear evidence that the terms of your series are getting smaller and smaller and smaller. Well, then it's going to converge. Well, what if it's greater than 1? The terms of your series are getting larger. It's clearly going to diverge. Now, it's whenever the limiting value is equal to 1 where we don't know, and we're going to have to look at those cases to determine that. Now, in this problem, we can just say, well, all right, my limiting value is going to equal the limit as n approaches infinity of the a sub n plus first term. Well, that's going to give me n plus 1 factorial divided by 9,999 to the n plus 1. Now, I forgot to mention, what happened to the factor of -1 to the n? Well, keep in mind, the ratio test says it's the absolute value of a sub n plus 1 over a sub n. So since you're talking about an absolute value, I don't have to worry about any alternating sign. You can completely ignore that term. So it's the absolute value of, you're just putting an n plus 1 into this fraction, you get n plus 1 factorial over 9,999 to the n plus 1. And then you're going to multiply that by the reciprocal of a sub n, which just gives me 9,999 to the n divided by n factorial. Now, I know that n plus 1 factorial means n plus 1 times n factorial. So this n factorial cancels with almost all of this, except for the term n plus 1 itself. That's where that came from. Similarly, this 9,999 to the n plus 1, that means I just have one more factor of 9,999 than I had in the numerator. That's why my denominator has 9,999 to the first power. Now, I need to take the limit of this expression, and you'll notice I took the absolute value off because all of these terms are positive anyway. But you say, well, as n goes to infinity, that numerator is infinity. Infinity divided by any finite number in existence, still infinity. So since that limiting value is infinity, our limiting value is clearly greater than 1, this series is going to diverge. So even if this limiting value would have been 2, you gotta said it diverged. This one super diverges because the limiting value is infinity. That literally means the next term is infinitely times larger than the term preceding it. That's this series gets large, and it gets large fast. For 22, this is our power series problem where we need to find the interval of convergence. So the difference in just your normal ratio test and number 22, where we have a power series, is now we have a function of x, where we need to find the values of x that will make this series converge. You say, okay. In order to determine that, make sure I go to the right thing here. In order to determine that in this problem, I go in here and say, well, all right, in order to find the values of x that make this series converge, I'm going to look at the ratio test. I know that the ratio test converges anytime the limiting value is less than 1. So I take the limit as n approaches infinity of the absolute value of a sub n plus 1. That's my 2 to the n plus 1 times x minus 2 to the n plus 1 over n plus 1, divided by a sub n. Well, I'll multiply by the reciprocal of a sub n times n in the numerator, 2 to the n in the denominator, x minus 2 to the n in the denominator. Now, I take this multiplication problem, I simplify it. I can say, well, this is going to become the limit as n approaches infinity. And I know that I'm going to have one more factor of 2 in the numerator. 2 to the n plus 1 divided by 2 to the n gives me a 2 in the numerator. Similarly, I'm going to have one more factor of x minus 2 in the numerator than I do in the denominator. That's where I have the x minus 2 to the first in the numerator. But then you have an n in the numerator and an n plus 1 as a factor in the denominator. And again, these two terms canceled with these, so they're gone. So this is my new simplified problem. I need to take the limit as n approaches infinity now. And you just say, well, n divided by n plus 1, that's going to reduce down to a fraction of 1 as n goes to infinity. And now these two terms didn't have an n in it. So you just say, well, that part goes off towards 1. A factor of 1 you can just ignore. And you say, well, this is going to become the limit. The limit has been taken. That's why the limit disappears from this step to this step. And you say it's just the absolute value of 2 times x minus 2. Now, that limiting value is going to show us that the series converges if it's less than 1. So I can say, well, it needs to be less than 1. I'll work on that here. It says series converges if this absolute value is less than 1. That means that what's inside 2 times x minus 2 needs to be less than 1 or greater than negative 1. Now solve for x. I divide by 2 everywhere. And then I add 2. Negative 1/2 plus 2 gives me positive 3 over 2. 1/2 plus 2 gives me positive 5 over 2. So now, what this is telling me is that I am 100% certain that this series will converge if x's values between 3 over 2 and 5 over 2. However, if x is 5 over 2 or if x is 3 over 2, it's going to make the limiting value 1 in which case the ratio test is inconclusive. So that's why I said, well, all right, we need to check the endpoints of 3/2 and 5/2. That's what I did down here. I checked the right-hand endpoint of 5/2 first. If I plugged a 5/2 into this function, you just say, well, all right, you plug a 5/2 in for x, and you're going to have 2 to the n times 5/2 minus 2 to the n. 5/2 minus 2 gives me positive 1/2 to the n all over n. Now in that numerator, 2 to the n times 1/2 to the n, that's 2 times 1/2 is 1 to the n. And if you have a 1 to the n, there's no point to even put it to the n. 1 to any power is just 1. So you say this is going to simplify down to 1 over n. But then you're like, but that diverges because that's our divergent p series, often called the harmonic series, where p is equal to 1. We remember that that is the smallest possible divergent series possible. Anytime the denominator has a power greater than 1, it would converge. 1 and less, it diverges. So we say, all right, that part diverges. What about the other value at the endpoint, 3/2? If I plug a 3/2 in, instead of that being 1/2 to the n, 3/2 minus 2 is a negative 1/2. You're going to have 2 to the n times negative 1/2 to the n. When you multiply that numerator out, you say, oh, well, you're going to have a factor of negative 1 to the n. And then you can say that changes everything because now it's an alternating series. And for an alternating series, all we have to show by the alternating series test is that the limit as n approaches infinity of the non-alternating part, which would be 1 over n, the limit of that non-alternating part is 0. Thus, the alternating series is going to converge. So we say this converges by the alternating series test. Since that sign is going to go positive, negative, it's going to eventually converge to some finite value. Thus, I can include the endpoint 3/2 in the interval of convergence. And the final interval of convergence answer I tried to squeeze in here. We put it in interval notation. This converges for values of x starting at 3/2 and including 3/2 since it converges there, going up to 5/2 and not including 5/2 since it diverges there. All right, guys, that will do it for this practice test. Please let me know if you have any questions. I'll be glad to help.